In this session, we are going to use a public dataset produced by the Ocean Biodiversity Information System, OBIS. It contains the historic whale catch records from the Australian whaling stations from 1925 to 1978. It contains 38,000 plus records, but we are going to use a subset, the subset with the data that corresponds to the most common caught whale, the humpback whale, that has 23,581 records. Okay, let's start with two important concepts, population and sample. We call population to the entire group of individuals to which the findings of the study are to be extrapolated. The individual members of this population are known as the units, and the units can be basically anything. Can be individual birds or animals or trees of a given species, can be plants or plots, can be people, can be households, can be businesses, schools, hospitals, whatever. The population must be fully defined, so the inclusion and exclusion criteria are clear to everybody. For example, we could define our population of whales as all the whales in the world, or the whales in Australian shores, or the humpback whales in Australia, or the female humpback whales in Australia, or so on. So the less strict the inclusion criteria, the larger the variability among the population. The stricter the criteria, the more homogeneous the population will be, but at the same time, the smaller the population, we can make generalizations from our sample. It's not always easy to clearly define the population that we are going to be dealing with. As an example, in the ordinary usage of the population of England, that we will denote the number of people living within the England boundaries, that maybe we get by a census, but people are born, people die continuously, some people move abroad, some people may come from abroad. So defining the population is not always something straightforward. We want to know something, a certain value, answer some questions about the population, but we cannot measure all the units in the population because usually time and budget constraints, but also because sometimes the measurement process implies that we have to destroy or kill the unit, and therefore this is not possible. So, for example, if we want to study the content of heavy metals in the liver of salmon, we have to catch the salmon, kill the salmon, analyze the liver, and we cannot do this for the whole population of salmons. Then what we do is to select a subset from the original population, and this subset is going to be the sample. We are going to measure, observe all the units in the sample, and we will use these observations, these measurements, to estimate the population value or answer some questions about this population value. A well-chosen sample would contain most of the information about a particular population characteristics. And we define the population units, and the population, the sampling units are basically the same, are the units within the sample. In this picture here, we have one of the samples collected, one of the tubes collected by NASA Perseverance rover in Mars that contains some sample from the soil and the rocks in Mars. So the procedure that we use to select the sample units from the population is called sampling. We collect the sample and we observe, we measure some characteristic from these units in the sample. We will then use this sample data to estimate some population characteristic. But the population characteristic is fixed, is always the same. However, the estimate we obtain from the sample depends on which sample is selected. Different samples will yield different estimates. And there are two desirable characteristics of the estimates that can be controlled when we are designing the sampling scheme. The first one is the precision of the estimate. How close we expect our estimate to be with respect to the true population value. The closer it is, the more precise the estimate will be. And precision is something that is controlled with the sample size. The larger the sample size, the greater the precision of the estimate. The second characteristic is being unbiased. An estimate will be unbiased if it's targeting the true, although usually unknown, population value. Possibly the estimate won't have the same value as the population value, but will be close to it, will be around it. We will obtain unbiased estimates using representative samples, and representative samples are achieved by selecting the units from the population using some sort of random process. Here we have the picture for situations. In the top row, we have biased results because they are targeting not the bullseye. The bullseye represents the target population value. The bottom row shows unbiased results because they are targeting the bullseye. The ones on the left show low precision in the estimate, regardless whether they are biased or unbiased, but it's still low precision because the variability around the true value is large. And in the right-hand side, we have great larger precision because there is small variability around the target. We select one sample, right, at random. But we could have selected other samples. We selected just one possible sample among many possible samples. And each sample would yield to have produced different results. The difference between the value that we obtain from the sample and the true, although usually unknown population value is caused by what we know or are known as sampling and non-sampling errors. Note that even if we call them errors, it doesn't mean that we have made something wrong or a mistake. It's just a statistical terminology. It's this difference between the estimate and the true value is the error. These errors are inevitable, and the sampling error comes from the fact that just a part of the population is included in the sample. We have just a small chunk of the population information in our sample. And therefore, the estimate will be different from sample to sample, and will be also different from the true population value. The sampling error affects the precision of the estimate. We will always have sampling error. This is something inevitable. If we are using samples instead of the whole data set from the whole population, we will have sampling errors and we will have to handle it. The great thing is that we know how to measure these sampling errors, and we know how to measure the precision of our estimate. The non-sampling error usually comes from the fact that we don't have a representative sample. We may have it not representative because, for example, in a fish survey, some selected sites may not be observed due to rough weather conditions, due to floodings, due to security reasons, because they are too far from the shore, or for any reason we didn't observe some of them. We may not observe, we will not measure all the units. For example, a non-response in a survey, or an animal or a plant that dies during experimentation. We are measuring the characteristic with measurement or recording error. For example, in the humpback dataset, there are 31 whales with length equal to 0. We can have larger or shorter whales, but we cannot have whales of length equal to 0. That's an impossible thing. So this is a measurement or recording error. And when dealing with humans, response bias is a source of non-sampling errors. It happens when a number of different conditions, social conditions or factors, usually may lead the respondents to provide inaccurate or false answers during the surveys, looking more to the desirability, what is desirable in their answer more than to what is sincere. Let's think about questions about drug use or sexual habits or cheating on exams, for example, all these we probably wouldn't answer sincerely. The non-sampling errors affect the accuracy of the estimates, the fact that they are biased or unbiased. They are also unavoidable, although they can be reduced, being careful during the design and data collection stages. Designing a sample process using a scientific approach can help to minimize sampling error and create estimates that are precise and unbiased. There are two broad families of sampling methods, the probabilistic and non-probabilistic sampling methods. On a probabilistic sampling design, every element of the population has a known non-zero probability to be included in the sample. In a non-probabilistic sampling plan, we don't have this feature. In a probabilistic sampling, because every element has a known chance of being selected, we then can obtain unbiased estimates of the population characteristics. And we can also work out the precision of the estimate. To do that, we need what is called the sampling frame, which is the list of all the units in the population, and to know also the probability attached to each one of these elements. Having this sampling frame is something that is not always possible. So let's have a look at the most basic sampling design, the simple random sampling. We have previously seen what happens when we take several samples from the same population, but when we conduct our research, we'll be able to usually get just one sample. So we have to make the most of it. Simple random sampling is the probabilistic sampling design in which every unique in the population has exactly the same probability to be selected, to be part of the sample. Simple random sampling is the most efficient design as it provides the most precise estimate of a population characteristic for a given sample size. And also those estimates are going to be unbiased. Yeah, the numbers of a lotto, for example, this is the simple random sampling example. In the simple random sampling scheme, and usually we can do this for other designs as well, the population mean is the best estimate for the population mean is the sample mean. The best estimate for the population variance is the sample variance. The best estimate for the population proportion or probability is the sample proportion. These estimates are best because they are unbiased and because they have maximum precision. Those estimates, though, provide a single value for the population characteristics. And that's the reason why they are known as the point estimates. If we do the simple random sampling in a proper way, we can expect that those are unbiased. However, we have already seen that the single value, the point estimate, may not be enough. We need also a measure of the precision of the estimate. There are different ways of measuring the precision, and the three most common ones are the standard error that is usually used for means or variances, the margin of error that is usually used for proportions, and confidence interval that is used for both. All of them are related, and if you know one of them, you can work out the other two very easily. Again, we talk about standard error, margin of error. The term error here is to measure the degree of precision or uncertainty in the estimates. One of the interesting characteristics of the precision measures that we have described above is that depend basically only on the sample size. Specifically, they depend on 1 divided by the square root of the sample size. Therefore, the larger the sample size, the more reduced will be the uncertainty measures. Large sample size, this standard error, margin of error, confidence interval will be very, very small. For a small sample size, these standard errors, margin of error confidence interval will be larger. When we add 1 unit to our sample, the gain in precision when the sample is small is large. When the sample is large, it's the gain in precision when we add an extra unit is very small. So at some point, there's a trade-off in between the cost of getting 1 extra unit and the gain in precision that we obtain with this extra unit. So since the precision of the estimate depends on the sample size, it can be established at design stage. So at design stage, we can define what precision we are going to achieve by selecting a sample size, or the other way around. When we define a sample size, we will get a precision for our estimate. It's interesting to realize that we do not need to take repeated samples to estimate standard error or margin of errors. There is enough information with it 1 single sample. And for a large enough population, the sample size to achieve given precision, it's a number. So you need 300, you need 500. It's not a proportion of the population. So if the population is larger, we don't need to have a larger sample size to achieve the same precision for the estimates. For smaller population sizes, we need to do some sort of correction to make sure that we don't have a sample that is larger than our population. The confidence interval. The confidence interval gives an indication of the degree of uncertainty of an estimate and helps to decide how precise a sample estimate is. The confidence interval specifies a range of values likely to contain the unknown population value. This interval is defined by a lower and upper limit, and the probability that the confidence interval includes the true population value is given by the confidence level. So we usually talk about 95, 99% confidence interval. The width of the interval depends on the actual precision of the estimate and the confidence level used. The greater, the larger the standard error will result on a wider interval, so lower precision. And the wider the interval, the less precise the estimate will be. We usually use the 95% confidence interval. 95% is the confidence interval that by far is most commonly used. However, we can calculate the confidence interval at any given level of confidence, such as 90%, 99%, or whatever we want. Why 95%? Basically, there are 2 kinds of reasons. One is historical reason, and it was 100 years ago in 1925 that the father of the modern statistics himself, Ronald Fisher, picked 95% as the confidence level because it was basically easy to compute at that point. But he said that this was an example, but shortly after him, it was taken as the standard. If we take 95% confidence interval, means that this confidence interval has the 95% probability of including the true, although unknown, population value. So if we repeat several samples, and for each one we compute the confidence interval, 1 sample out of 20 is expected to not include the true population value. 19 out of 20 will include, 1 out of 20 won't include. If we want to be more confident that our confidence interval includes the true value, for example, 99% instead of 95%, increasing the confidence level will imply that the confidence interval gets wider to include more values, to be more confident that the confidence interval includes the true population value. So the second reason why 95% is a standard, the first one was historical reason. The second one is because it's a good trade-off between being almost sure that it will include the true population value and having an interval that is wide enough to be useful. We don't get too wide intervals that include everything. That would be unusable. 100% confidence interval is something that we never compute because it would have basically infinite width. For the purpose of demonstration, let's get a sample of 50 whales from our data set of 23,580 whales and measure the length. And this is a confidence interval for the length. The true population value is this value here, 13.31, I think. And this is the confidence interval. It includes the true value. This is a 95% confidence interval. If we add a new sample, we get a different confidence interval, a different sample mean, and a different confidence interval, which again includes the true population value. If we keep producing samples, repeated samples, at some point, we will get one that does not include the true population value. So we have produced 20, still none. So this is a probabilistic thing. So here we have the first one to make it easy to identify them. Those in red are those that do not include the confidence interval, does not include the true population value. So this is a probabilistic thing. We can get one sample, at this one sample do not include the true population value, or we can get several of them before we get the first interval that does not include the true population value. This is a probabilistic thing, but in the long run, if we produce a very large number of samples, and for each one we computed the confidence interval, 95% would include the true value. So again, the 95% is a good trade-off between being fairly sure, 95% confident that it will include the true value, and not being extremely wide, that wouldn't be useful at all. If we increase the sample size from 50 to 200, now the confidence interval is going to be half the width of the previous ones, because we know that the width of the standard error and the width of the confidence interval depends on 1 divided the square root of n. So if the sample size is 4 times larger than before, the standard error will be half of it. And if we go to very big sample size, we will get even narrower, so more precise estimates. But it doesn't matter how precise is our confidence interval. If it's a 95 confidence interval, in the long run, 1 out of 20 or 5% of our confidence intervals will not include the true population value.